Now we're up to the biggest question that I wanted to answer with this this set of videos. The question is, if these orthogonal bases that we've been talking about, or orthonormal bases, if they're so nice, how do we generate them? So if we're given a basis, how do we actually go about changing it in some way, sort of turning it into an orthogonal basis? And of course you want to do this in some, what I've called here, a coherent way. Alright, you don't just want to completely scrap the original basis and start fresh with an orthogonal one. Is there some way that you can take the given basis, the information that's in the given basis, and just adapt it to turn it into, sort of evolve it into an orthogonal basis? Right, so what I mean by this sense of coherence, right, in some coherent way, if we were to start with, let's look at a two-dimensional basis for simplicity. Right, so if we were to look at the basis 1, 1, and the basis, let's say, 3, 1. Alright, so if we look at a picture of this, 1, 1 looks like that, and 3, 1 looks something like that. That's a terrible picture, but you get the idea. Alright, so your two basis vectors look like this. They're clearly not orthogonal. And if we were to just go ahead and scrap this basis and say, well, I know that the standard unit basis is an orthogonal basis, so why not just use that? Well, you're completely throwing away the information that you had in the original basis. All right, this new basis, or just the standard unit basis, looks like those red vectors, and those just aren't the same, right? There's really just no relationship between them, at least not any sort of useful relationship between the two bases. So the idea is not to just throw away the original basis entirely and start from scratch. The idea is that you actually want to take the original basis, and can you do some procedure to it that will turn it into an orthogonal basis for you? And this is what I mean by this sense of coherence. All right, you don't just want to throw it all away and start from scratch. You'd like to adapt the original basis in some systematic way into an orthogonal basis. All right, so that's the two things we're going to talk about in this video. First of all, how does that process of adaptation actually go? Right? How do we actually generate this orthogonal basis? And in particular, what do I mean about this sense of coherence? All right, so how can we sort of make this sense of coherence between these two bases a rigorous idea? Okay, so again, let's start off with two vectors. So suppose we have a basis that has two vectors in it. V1 and V2. And we want to make this, we want to turn this into, right, adapt this into an orthogonal basis. All right, so we want an orthogonal basis. That's the idea. All right, so the way we're going to start out, you have to start somewhere, and you want the original basis to inform whatever you're about to define. So we're going to start off, and also this new basis, just so they have their own names, we're going to call them U1 and U2. All right, so U1 and U2 are going to be the orthogonal basis vectors. So we're going to start off, because we have to start somewhere, we're just going to let U1 just be V1. All right, they'll just keep V1 the same. Now, can we figure out what U2 should be? All right, so what should U2 be? All right, and U2 should be, right, remember here, U2 should be orthogonal to U1 because it's supposed to be an orthogonal basis. All right, so what should U2 be here in order to be orthogonal to U1? Well, we can draw a picture, sort of what's going on here. Right, we've got maybe V1 down there, which is the same as U1 because of the way we defined U1 is just V1. And we've got V2, our second basis vector, pointing off somewhere else. So remember, this is a thing that we have seen many times now in this class. Right, we've got these two vectors, and what we want to do is figure out basically the part of V2 that is exactly orthogonal to V1, which is U1. Right? Because this is what we're really after. We're trying to replace V2 by something which is just orthogonal to V1 or U1, whatever you want to call it. They're the same vector. All right, so we're looking for something that is purely orthogonal to this. And again, we always want to have this idea in the back of our mind of doing this in a coherent way, a way that doesn't just scrap all the original information in the original basis, but rather uses it to generate orthogonality. And so what we want to do here is figure out this red vector that I've just drawn in this picture, because that's going to be the part of V2 that is orthogonal to V1. All right, so this is what I mean when I say the sense of coherence. We're going to use V2, figure out what part of it is orthogonal to V1, and that's what we're going to call U2 in our orthogonal basis, U1, U2. All right, so that's how we're going to generate U2. And now we know exactly how to do this. We've done it a bunch of times. First, we could figure out the projection onto, well, let me use the language that I've just developed. The projection onto U1 of V2. That's this blue vector that I've drawn here. And because of that homework exercise that you did on the first homework in this class, which has come up, I think this is the fourth or fifth time this has come up in this class, we know that V2 can be reconstructed via the projection onto U1 plus, and that's, maybe I should draw that in the color that I've used. Right, this is the projection onto U1 plus this vector in red that I'm just going to go ahead and label as U2 right now. Right, this is the vector that we want. That's U2 right there. All right, in other words, if I solve for U2, right, U2 is going to be the original vector V2 minus its projection onto the first new basis vector, the projection onto U1, which is just the projection onto V1, but I want to call it U1 because this is going to be important for us moving forward. All right, so this is our main formula right here. That is U2 for us. All right, so the new basis, and I'm going to use the orthogonal shorthand here, the perpendicular sign shorthand. This is our new orthogonal basis, is U1, U2, where U1 is just equal to V1, and U2 is the original V2 minus the projection onto U1 of V2. All right, so this is how you generate these vectors, right? In the colors that I used. u2 is this red vector in the picture, and u1 is just v1. I didn't do anything to that, right? Just leave that one alone. And one small side note that I want to make here is that if you really want an orthonormal basis, as opposed to just orthogonal, right? So if you want orthonormal, well, do this procedure to figure out the orthogonal version of the basis, and then you can make it orthonormal by just unitizing. All right, so when you're all done with everything else, just unitize at the end. All right, and if you write out this this formula, right, u1 is just equal to v1, and that's a definition we're making, right? We're defining u1 to be v1, and we're defining u2 to be the original v2 minus the projection onto u1 of v2. And you can write out the formula for this because we know the projection formula. This is just u1 dot v2 over u1 dot u1 in the direction of u1. All right. And in the very specific case where you unitize everything as you go, so if u1 were a unit vector here, then remember that u1 dot u1 is just the magnitude of u1 squared. And if that were a unit vector, that would just be 1. So actually your denominator wouldn't be there. It would just be u1 dot v2. And again, this is just one more way that orthonormal sets, orthonormal bases, are nicer than any other kind of basis. Okay? So this is how this would work for two vectors. And this leads us to the first sort of really interesting question. What happens if we have three vectors? Right, so what happens if we have a basis v1, v2, v3? Well, the beginning of the procedure is going to go the same way. All right, so this is what you might call an inductive procedure, sort of an iterative procedure is how you might think of it. We always start it off the same way, and then it just becomes more complex as we add more vectors into the mix. But it's always going to start out the same way. We're going to let u1 be equal to v1. That's the same as it was before. If you want this to be a unit vector, you can go ahead and unitize it. All right? I'm not going to do that just for I think clarity of the video. I think it'll be a little bit clearer if I don't unitize it at every stage. But just always know that if you want to unitize these things, you can. All right. So we're going to let u1 be v1. We're going to let u2 be original v2 minus projection onto u1 of v2, just like we did before. Now the question becomes, what do we do with u3? All right, how do we figure out u3? So we want u3, which is orthogonal to both u1 and u2. All right? And it shouldn't just be any old vector. It should be something that's generated from the original basis. Right? This is that sense of coherence that I mentioned. So it should be something that's generated from the original basis. If we only have three vectors, then in saying that we want something that's orthogonal to both u1 and u2, well, we only have one dimension left to work with, so we're really not saying that much. We only have one option, really. It has to be the normal vector, or parallel to the normal vector. to the plane generated by u1 and u2. But regardless, this sense of coherence is more important when we have higher dimensions. So we want a u3 that is perpendicular or orthogonal to both u1 and u2, and we want to generate it using the original three vectors from our basis, v1, v2, v3, or in this case, the two new vectors, u1 and u2, and the original vector v3. Okay, so the idea is that you've got u1 and u2 just sort of sitting here, right? You've already created these vectors. They are orthogonal to one another. I'm trying to draw a three-dimensional picture here, which is why my orthogonal vectors don't necessarily look like they're orthogonal. But you just sort of have to imagine that there's a weird perspective shift going on here. And u1 and u2 are orthogonal to one another. And then you've got this original basis vector v3, which is just sort of flying off somewhere else in space, right? They're all rooted to the same place, of course, because we always imagine these vectors as being rooted to the origin. But it's sort of going off on some other, some completely different orientation than the plane that u1 and u2 live in. All right, so these two vectors, u1 and u2, really span a plane. So let's go ahead and put that plane in this picture. All right, so let's imagine that this is the plane spanned by u1 and u2. And v3 is just sort of pointing off in some other direction entirely. All right, so the same kind of idea is what we want to use here, right? The same idea that we used before, if I go back a page, was in this picture right here. Right, we take the original vector that we start with, which in this case we called u1. It was v1 and we relabeled it as u1. And we want to figure out this part of v2 that's orthogonal to u1. And we're going to use the exact same idea here. All right, so what we're going to do is figure out the part of v3 that is orthogonal to both u1 and u2 at the same time. In other words, that's going to be the part of v3 that is orthogonal to this plane spanned by u1 and u2. All right, so that's going to be our vector right there. And you can draw a very similar picture to that projection picture that I had in the last on the last slide. If I draw in the projection vector, it would look something like this. All right, so this this thing in blue here, this would be the projection onto what I'll call S of v3, and here S is the span of u1 and u2. And S in this case is this entire plane. All right, so again, the span is just a set of all linear combinations. So the set of all linear combinations of u1 and u2 would be a two-dimensional linear object, meaning it has to be a plane. And so S is, this entire plane is what I'll call S. So this blue vector is the projection onto the plane of v3. You could think of this as being like the shadow cast. If you shine a light perpendicularly down from above onto v3, the shadow that v3 casts onto the plane below it would be this projection vector. Okay? So that's given in blue, light blue, that is. And this this purple vector is what we want. This is exactly, that was a terrible 3. This is this vector u3 that we're after. Right? This is going to be the part of v3 that is orthogonal to both u1 and u2. And the easiest way to verify that it's orthogonal to both u1 and u2 simultaneously is making sure it's orthogonal to the span of them. meaning orthogonal to the plane that they define. Okay, so this is the biggest sort of leap in understanding that you have to make from the previous case to this case, the two-dimensional to the three-dimensional case. So the question becomes, how do you calculate this projection vector, right? How do you figure out what that shadow cast onto this plane should actually be? That is a question, and we have to answer it if we want to answer this question. So you could use some sort of idea to figure out U3. You could use some sort of idea about cross products, because cross products generate a vector that's orthogonal to the two that you plugged into it, whose direction is determined by the right-hand rule. You could use an idea of cross products. However, the cross product is really only well-defined in 3 dimensions, and I would like this process that we're going to do to work in any dimension. So I don't want to take the easy way out right now and use the cross product. Instead, I want to do something that's going to be generalizable to any dimension that we work in. All right, so we want to know the formula for this projection vector, because then U3 will just be original V3 minus the projection onto the subspace, the plane spanned by U1 and U2 of V3. All right, so it's going to be V3 minus its shadow. So this means that if we want to calculate U3, all we need to know how to calculate is this projection onto a plane. All right, so this is the thing that I want to do next. How do we actually calculate this projection onto a plane? So the thing to notice here, I'll illustrate the base point of that thing in red. Right, so that base point, which is where the light blue projection vector points, and where U3, the purple vector as I've drawn it, originates. That vector, that point in the plane is the nearest point from the tip of V3 down to the plane. All right, so this is the closest point between the plane itself and the end of V3. So what we're actually looking for, right, to find the projection onto S of V3, we actually want to find the point in S, which is that plane, of minimal distance to this remaining vector V3. And now, minimal distance, this is an optimization problem. We want to find the minimum of something. So the way we're going to go about this is by recognizing that anything in S can be expressed as some constant A times U1 plus some other constant B times U2. Right? It's just a linear combination of U1 and U2. This is how S is defined. So what we want to do, right, we want the A and the B, the coefficients on U1 and U2, which minimize the distance from AU1 plus BU2 to our vector that we care about, which is V3. All right, and this is the this is the distance from V3 to the plane S. All right, so we want to minimize this thing. We did a bunch of videos minimizing distances, and this was like our stat application problems. And we saw in every single case there that it is much easier to minimize the distance squared as opposed to the distance itself. So we're going to do that here as well. We want to minimize this square distance. In other words, we want to solve this least squares problem. All right, so what point in the plane, this is going to answer what point in the plane is closest to V3. Answering that will tell us the formula for our projection vector of V3 onto the plane. All right, so this, rather than writing it out in formulas, which of course we can do, really complicated vector formulas, I mean, we can instead recognize that a distance squared is something dotted with itself. All right, so this is AU1 plus BU2 minus V3 dotted with itself. All right, those are equal. And so we want to minimize this dot product of a very complicated looking vector with itself. Now this we can do. Right, this is a function. Remember what we're trying to do here. We're trying to find a and b that will minimize something for us. So this thing that we're defining is a function of a and b. U1, U2, V3, these are all fixed things. They're, if this were a real problem, you would have numbers in front of you. You would know what those things were. A and B are the unknowns. So what we want here is to minimize this. We need to take its gradient. Right, we need the gradient of this thing. And the gradient, the reason why I'm harping on what the variables are, this is going to be a derivative with respect to A and a derivative with respect to B. Okay? So, the way this works, we want to calculate, for instance, the derivative with respect to A of this whole expression up here. All right, we want to calculate the derivative with respect to A of that thing. And I haven't talked about this too much. It did come up at one point, but I sort of just mentioned it and moved on. But there is a form of the product rule for dot products when taking derivatives inside of dot products. So the way this is going to work is we're first going to differentiate this first term with respect to A and then dot it with this second term left alone. And then we're going to do the opposite and add them together. Not the opposite, but the other order and dot them together. All right, so this first one, the derivative with respect to A of this thing is just going to return U1. And that's going to be dotted with the second thing left alone, which is AU1 plus BU2 minus V3. And now add the first thing left alone, which is AU1 plus BU2 minus V3, dotted with the derivative with respect to A of this term here, which is just going to return U1. And notice that these two terms are really saying the exact same thing, just dotted in different orders, but the order in which you dot things doesn't matter. So this is really the same thing as 2 U1 dotted with AU1 plus BU2 minus V3. And the derivative with respect to B of that same thing well, this is just going to be the exact same thing, except when we take our derivatives with respect to B, we're going to be isolating the U2 terms instead of the U1 terms. So we're going to get something very similar, and I'll leave this for you to double check as an exercise. But you end up with 2U2 dotted with AU1 plus BU2 minus V3. All right, so these are your derivatives with respect to A and with respect to B. Before you begin the next video, I want you to work out what these are. Go ahead and take these dot products by distributing these in and see what you come up with. Okay, you're going to get a pretty nice formula, and even better than that, it's one that you should recognize. All right, so try that out before you start the next video.